So, hello everyone. So let's solve an interesting problem. This problem I find it very useful to explain some nice concepts about the interaction between the force dynamically induced EMF, the circuits, and the magnetic field. So, a conducting rod AB makes a contact with metal rod AD. So, if you go to the diagram, so what do we have here? So, this is a metal rod. So, let me do some markings. So, this is a metal rod. Okay, so this A to D is a metal rod. Okay. So, and also that is AD is a metal rod, and also BC is also a metal rod. AD and BC, two metal rods. On one side, they are connected by a 4 ohms, zero point 0.4 ohms resistance, that is DC, and the other side, they are connected by a rod AB. Okay, so that is what is the first sentence. So, which are 50 centimeters apart in uniform magnetic field of. So, what is the magnetic field? So, if you look at this cross marks here, so there is some cross marks you can find here. So, it means that there is a uniform magnetic field. So, imagine that this A, B, C, D forms a plane, that is the screen of your monitor, or the page of the book, and the magnetic field is entering into the book from the top perpendicularly into the plane of ABCD. So that is the direction of the magnetic field. That's why we use the cross symbol. So again, this is a convention. Cross means something which is entering into it. Okay. So whereas a dot means something which is leaving the screen. So if there is a magnetic flux coming out of the screen perpendicular to your face, then we represent it as a dot. But then in this example, the magnetic field is entering the screen. Okay, so that is the direction of the magnetic field. So as you can see, AB is perpendicular to the direction of the magnetic field, which is entering into the screen. And the magnetic field B is nothing but 1 Tesla. Okay, so that is given here 1 Webers per meter square. Perpendicular plane ABCD. The total resistance of the circuit ABCD is 0.4 ohms. Okay, so I have just explicitly mentioned resistance is 0.4 just to avoid the confusion, that there is a resistance between A to D. Now, this is the equivalent resistance of the entire circuit ABCD, so there is no other resistance involved anywhere, and it is assumed to be constant. Now, what is the direction of magnitude of EMF induced in the rod when it is moved to the left with a velocity of 8 meters per second? Now, this particular rod AB is moved towards left. So this rod is moved towards left at the speed of 8 meters per second. Now you can ask the question how it is moved, why anything is moving. So you know Newton's laws of motion. If some force is acting, only then this rod will move, otherwise this rod will remain in the rest position. So some force F is acting on this. So let's call it F in. So this is the input force that is moving the rod AB away from the this one, but it is still connected to the rails AD and BC. So a a conductor which is closed and it is placed in a magnetic field and it is moving, so obviously EMF is induced. So that is the first question. What is the direction and magnitude of EMF? Let's do the magnitude of EMF first. Okay. So what is the magnitude of EMF? So we know that EMF induced is nothing but B I V sine theta. In this case, sine theta is 90 degrees because magnetic flux and the conductor are perpendicular to each other. So 1 Tesla multiplied by BLV. This is not I, this is L, length of the conductor. So what is the length of the conductor? It is 0.5 meters. So 50 centimeters or 0.5 meters multiplied by V is the velocity. Okay. So velocity is 8 meters per second. It's given in the question. So this value is 4 volts. Okay. So 4 volts of EMF is induced in this particular conductor AB. You might ask, what about the EMF induced in AD? Because AD is stationary, there is no EMF induced in AD. Similarly, BC is stationary, DC is also stationary. So this part of the network is stationary, so no EMF is induced in it. And this part of the network is moving, so therefore in the conductor AB, some EMF is induced. Okay. So that magnitude of EMF we have calculated. So now the question is, what is the direction and magnitude? So we have only calculated magnitude. The question is, what is the direction? So in other words, there will be some current flowing in this circuit. So is the current flowing from point A to point B or point B to point A? What is the direction of the current we need to identify? Now remember, sometime back in this channel we mentioned Fleming's left hand rule and Fleming's right hand rule. So is this a generator or a motor? So because I am giving mechanical input, so force input is my mechanical input power. So this is nothing but an electrical generator. Some voltage is generated, that is 4 volts is generated. So for generator we use Fleming's right hand rule. Okay. So for motor we use Fleming's left hand rule. Okay. So remember this. In fact, I have made separate video about Fleming's left hand rule and right hand rule. So you can search on my channel. You will be able to find it. Now for generator, Fleming's left hand rule. Sorry, for generator right hand rule, and for motor Fleming's left hand rule is used. So to determine the direction of EMF and the direction of the current, we use the Fleming's right hand rule. So let me draw the right hand. So you just look at your own right hands. You can pause the video and look at your right hands, keeping your thumb, first finger and the middle finger perpendicular to each other. So I draw it something like this. So this is the thumb and this is the first finger. And this is the middle finger, and then just the other two fingers are folded, and then this is the palm. Okay. So this is your Fleming's right hand rule. And how do you remember? This is your right hand. So how do you remember which finger is for what? So that is nothing but your FBI rule. Okay. So or you can remember famously this full form, Federal Bureau of Investigation, FBI. Okay. So that's just a tip to remember it. So this is F, this is perpendicular to it is B, and perpendicular to it is I. So F means force. Okay. B means flux. So remember, B is the symbol for flux density, and I means current. Okay. So you know I is the symbol for current. So if now which is known, which is unknown. Okay. So for the Fleming's right hand rule, as I said, it is a generator. So current generated is unknown, whereas flux is known and force is known. Okay. So if you keep your right hand oriented in such a way that the force direction you are pointing it correctly and flux direction you are pointing it correctly, these two are the knowns, then the unknown current you will be able to know. So if I just go up and apply Fleming's right hand rule. Okay. So to this diagram. Okay. So how do I apply Fleming's right hand rule? So the force here it is upwards, but actually, so if I simply write it, force and then this is flux and then this is current. Okay. So this, if I think I need to rotate this by 90 degrees, then the force will be like this, and flux is completely downwards. So I use a cross symbol. As a result, because of your right hand, the current direction will be downwards. So please try with your right hand, align your right hand like this, okay, and then in front of your computer screen, you'll be able to find that the current or EMF induced will produce current in such that it is moving towards downwards. So what is the equivalent circuit we have now? So the equivalent circuit we have now will be something like, the negative will be on top, the positive will be on down, and this is my A, and then this is B, and then this is my 0.4 ohms resistance, this is D, and this is C. So just as per the diagram above. Okay, so why I put the positive terminal downwards is because the current should be leaving this positive terminal. So that is the direction I am keeping. So what is the current? So simple Ohm's law, the EMF is 4 volts we know. So this is 4 volts. So I equal to 4 volts. I equal to V by R. So 4 by zero point 0.4, that is 10 amperes of current. Okay. So when I move this conductor left with 8 meters per second, 10 amperes of current is flowing in this one. 10 amperes is flowing here, 10 amperes is flowing here, and 10 amperes is flowing here. So this is the direction and magnitude of the current. So if I go back, so the part A of the question is completely solved. So let me mark it with green. Part A is solved. Now what about part B? What force is required to keep the rod in motion? Okay, now the rod is already moving at 8 meters per second, but then in order to continue that to move in 8 meters per second, some force is required. The reason is that you see a current carrying conductor AB is placed in a magnetic field. It will experience a force. Okay, so that force we have to counter it. Okay, so let me redraw the figure so that you can understand it. What is happening? So this is AB carrying a current of 10 amperes, and it is moving with a velocity of 8 meters per second. And in the presence of magnetic field, the magnetic field is perpendicular to the plane of the screen. Okay. So under this, so now you see a current carrying conductor is moving in a magnetic field. Okay. So an EMF, a force will be developed on the conductor. Okay. So current carrying conductor placed in magnetic field experiences force. So now I want to know what is the force that is being experiences. So here what is the input? So the input is current. Okay, so this is input. Input is electrical and the output is mechanical. Okay, so this is the output. So that is nothing but this is a motor. So when you want to determine the direction of the force in a motor operation, you will use the Fleming's left hand rule. Fleming's LHR, left hand rule. So again now look at your left hand and then we'll just draw the left hand now. So again the same technique to draw the left hand. You draw the thumb and then you draw the first finger and then you draw the middle finger. Then you draw the two other fingers and then just draw the palm. So this is your left hand. So what does each finger represent? So again same F, B, I. So F means force, B means flux, and then I means current. Now I want to determine the current is known. Okay, so this is known and the flux is known. So now I want to determine what is the force acting on this. Okay? Now if you can imagine, see here the current is going downwards and here the current is going this way. So if I just reorient my left hand in such a way that the current is again vertically down. So right now it is F is up and B is into the board and then I is right side. So this is exactly the same thing. Now, but then if I want to align with the current AB, current is downward. So if I just rotate this figure by 90 degrees, so I get current to be downwards and the flux will be into the board and the EMF will be, sorry, the force will be towards the right side. Okay. So a force is generated on this. This is F out. So some kind of output force is generated on the conductor AB. Earlier I mentioned F in. Okay, so this was F in. Some input force was required to move the conductor at 8 meters per second. Now to oppose that input force, an output force F out is being generated. So both generator and motor actions are going on. So this is quite interesting in that sense. Now how much is the value of F out? Okay. So the force generated can be calculated using the formula BIV. Okay. So BLV is the EMF induced in a dynamically uh, diameter induction, whereas the force is nothing but BIG. So this is the, sorry, BIL. I'm just we have not derived this formula, so but then we'll just use it for now, and then later on in some other video we'll be deriving. So this will be newtons. So my flux is, so if I go back to my problem, the flux is 1 Tesla. Okay, so I'll write it 1 Tesla multiplied by current is 10 amperes. Here it is there. So 10 amperes multiplied by length. It is, the length is zero point 0.5 meters, 0.5 meters. So this total thing 1 into 10 into 0.5 is 5 newtons of force. Okay. So the output force is 5 newtons. It's 12 so o'clock. To summarize what is happening, there is a conductor AB placed on a rail, and the rail is closed with zero point 0.4 ohm resistance, and there is a magnetic flux perpendicular to the plane. Then there is an input force F in such that it is this conductor AB is moving at 8 meters per second. Okay. So as a result, 4 volts is induced in this conductor, and the 10 amperes of current is flowing downwards. Okay. So as a result of this 10 amperes current and the flux, another force is being generated. That force is F out. Okay. So in order to maintain 8 meters per second, obviously, now to maintain the same velocity, both the force, the net force should be 0, then the velocity will be maintained. Again, remember the Newton's laws. The velocity remains constant as long as the net force is 0. So therefore, F in will be equal to F out. That is the magnitude, just that this direction is left and this direction is right. Okay. So the input force required is 5 newtons. So by the way, if I go back and look at the third part of the question, see what is the force required. I am looking at the B part. What is the force required to keep the rod in motion? This also we solved it, and the answer is 5 newtons. Now compare the rate at which mechanical work is done by the force F with the rate of development of electric power in the circuit. Okay, so let's see. What is electric power in the circuit? So electric power is nothing but I square into R. So 10 square into 0.4. So that is how much? 100 into 0.4, that is 40 watts. Okay, so this much power is generated. Now what about the this is electrical power, this is the result or output. Now what is the input? Input is 5 newtons of force, and the 5 newtons of force is being applied on an object which is moving 8 meters per second. Okay. So see, work done is nothing but force into distance. Okay. So work done divided by time is nothing but force into distance by time. I am just multiplying both sides by time. And what is work done by time? So work by time is nothing but energy. Sorry, work by time is nothing but power. So work itself is energy. So this is power. So this is mechanical power input. Okay. So is nothing but force into distance by time is velocity. Okay. So I know force is 5 newtons and velocity is 8 meters per second. Okay. So that means 5 into 8 is 40 Newton meters per second. Okay. So this is the mechanical input power. Now what is 40 Newton meters per second? Newton meters per second. Newton meters per Newton meter is nothing but joules per second. So that is nothing but 40 watts. So needs to be strong with your units. So now you see something very interesting. The electric power output is nothing but 40 watts, and the mechanical power input is also nothing but 40 joules per second or 40 watts. So basically, what you are looking at in this diagram is nothing but an electric motor. Okay, so I am moving this AB, and because of my motion, I am doing some work, and that work is being dissipated as the current in this resistance. Okay, so I hope by solving this problem you understood some concepts. This problem has a lot of interesting stuff. It is having a working principle of motor. It's having a working principle of generator. So how to apply Fleming's left hand rule, how to apply Fleming's right hand rule. So many things are there in this short problem. So it is very interesting. I hope you will learn something from understanding this problem. We'll see more in future videos.